My name is Kyle Kelly, and I'm a security researcher at Semgrep, specifically on the supply chain security team. For those of you less familiar with Semgrep, it's a popular open source project that we have built a platform on top of to offer static code analysis, supply chain security, and now secrets detection. Additionally, I'm the founder and author of Cram Hacks, which is a weekly newsletter dedicated to supply chain security. And really, I live and breathe this stuff. That's about all I do. I dream about supply chain. But as far as my background goes, I have a master's degree in computer science from Georgia Tech and a number of cybersecurity certifications, largely due to my background in penetration testing and incident response. So I spent a good amount of years breaking things and validating risks, whereas I'm now on the other side, helping Semgrep customers identify vulnerabilities that matter. So as far as the agenda goes, I'll do a quick recap, which I've broken up into 3 sections. So we have discovery, prioritization, and remediation. There should be no real surprises there, as that's the standard vulnerability management workflow for the most part. But as we dig into it, I'll be pointing out some key details while also providing some research-based evidence on how to effectively approach each of these. Additionally, roughly halfway through this presentation, I'll be showing you a demo of how our researchers write Semgrep rules and how that benefits our customers. We'll also get into analyzing a security advisory, Semgrep Playground, the app itself, and integrating Semgrep into your CI/CD. So let's get into it. So what is a software dependency? Well, by definition, a software dependency is a specific module, library, or software package that another piece of software relies on to function correctly. In essence, with the help of dependency management tooling for downloading, version management, etc., dependencies enable reuse of code at scale, and that just drives efficiencies across the board. Of course, there are both internal and open source dependencies, but for the most part, open source dependencies are almost definitely making a far greater impact at your organization. So taking a closer look at the likelihood of that statement being true, I pulled some data from Sonatype's 2023 State of the Software Supply Chain Report, the Linux Foundation, and the GitHub Security Advisory database. And firstly, to set a frame of reference in regards to scale, in 2022 alone, GitHub recorded over 52 million new open source projects. For dependencies specifically, we can look at NPM as an example, which hosts somewhere around 3 million unique packages. Now, NPM does by far host the most unique packages, which makes sense given JavaScript's use cases, but others like PyPy are still hosting about 500,000 unique packages with over 5 million releases after accounting for different versions. So that's still a ton. That said, it's really no surprise that over 90% of organizations use open source software in some shape or form, but maybe a more interesting data point is that 70 to 90% of your average application comprises of open source code. That said, there is one major caveat to that statement, which is that although many sources will reference the 70 to 90% figure, in actuality, the coverage is likely to be much less when you consider active code or lines of code that are actually executed by the application. That's just because a lot of open source dependencies have many, many lines of code, but you rarely ever, if ever, use all of them. And so the 70-90% figure is actually saying, hey, you're using this dependency, you must be using all those lines. But we know in reality that's not the case. Now, looking at vulnerabilities, there's also a ton of these. In 2022, there were just about 25,000 total CVEs assigned, and this number is trending upwards for sure, but we don't necessarily want to use CVEs as a single source of truth for supply chain vulnerabilities. Firstly, many CVEs are for commercial applications or standalone projects. Secondly, the CVE process is a bit painful in comparison to more simple methods, maybe like GitHub Security Advisories. So I usually encourage taking a look at the GitHub Security Advisory database, which pulls in issues from many sources, including NVD for CVEs. You also have to consider forked repositories in the open source space. Many major projects get forked. And if you're only looking at the CVE, you may only see that the major project is affected, whereas the forks may also be. So as the last time I checked, there were about 215,000 total advisories, which get separated into reviewed and unreviewed. So I'm going to narrow in on just the reviewed, which implies they've been vetted as legitimate. And that leaves us with roughly 15,000 security advisories. It's worth noting that roughly half of all reviewed security advisories in the GitHub Security Advisory database were either a high or a critical severity. Now, in my experience with reviewing thousands of advisories, anything less than a high severity can usually be safely ignored, especially when you still have highs and criticals in your environment. Other metrics such as the Exploit Prediction Scoring System, EPSS, or CISA's Known Exploited Vulnerabilities Catalog, the KEV, can also be used to prioritize vulns based on their likelihood of being exploited. So moving along, let's take a look at how to manage these vulnerabilities. So here's an example of just 7 projects which I've run Semgrep supply chain on, but without our reachability analysis filter enabled. That's intended to be a one-to-one matching of what you would see using something like Dependabot, but I'll be walking through what we do differently to make this number much more palatable in just a few slides. Now, 2,500 might seem like a little or a lot, and that's just going to depend on the size of your projects, how many dependencies you use, etc. But to put it into perspective, I've seen orgs with a total vulnerability count in the high 6 figures. So hundreds of thousands of vulnerabilities brought in by the dependencies used in their projects. Hopefully you're already using some sort of supply chain security tooling and have a general or rough idea of your magic number. For those of you with a big magic number, it's no surprise that Sonatype's 2023 report suggests supply chain attacks are increasing at a rate of 742% per year. That's pretty crazy. And just based on that number and the research I've done on malicious packages and things like that, it's definitely evident that the threat landscape and the threat actors are getting more complex with their attacks as well. So they're definitely seeing this as a major opportunity. But of course, they always follow the path of least resistance. That said, let's take a look at prioritization. So the likelihood is that you're using some tool other than Semgrep supply chain, if any. So your security staff or developers are likely to approach the problem with questions such as these, especially the obvious ones, which are, are we even using this function, and is it even exploitable? Then they'll likely spend valuable time and resources only to learn the code does not use the vulnerable function at all, thus making it unexploitable. Or my personal favorite, the vulnerability is a critical severity, but it's a regular expression denial of service vulnerability, and it's currently impacting internal application. So definitely not a priority. But open source dependencies enable impressive efficiencies. So any time spent investigating these questions that could be otherwise answered really takes away from that value. So now let's touch on how reachability offers near effortless prioritization. And so in the traditional sense, Semgrep supply chain still falls under the dependency scanner category, no different than a Dependabot or OWASP dependency check or NPM audit, just to name a few. So using a traditional solution like those mentioned, they'll take a vuln database and see thousands of vulnerabilities. Then they report the hundreds which impact your dependencies by looking at what versions you're using. However, instead, you can introduce code scanning reachability and narrow down from the hundreds to just the tens that results in an actual vulnerable usage. Otherwise, meaning the vulnerability rests in your code. So the major difference here, which we'll get into a bit deeper in a moment, but the traditional scanners are really just looking at, hey, what dependencies are you using? What versions are you using? How do those relate to a known vuln database? Now, the reachability component introduces that prioritization step to determine, are you actually using this vulnerable function in your code? So the magic sauce and how we do this is in our usage of the open source Semgrep engine, which also powers our other commercial products. This enables our researchers to write Semgrep rules that detect the vulnerable usage of dependencies. And if you've ever used Semgrep, whether it be the paid version or open source, you probably know how easy it is to write Semgrep rules. And if you're not familiar, don't worry, because I'll be going a bit more into detail on that during the demo. But as you can imagine, it's fairly simplistic, which enables our researchers to pump out a ton of rules to give our customers the best coverage. So for now, let's move on and discuss software composition analysis, often called SCA, which is ultimately the prioritization enabler. Afterward, we can look at some more research backing our claim here. which suggests reachability reduces thousands of alerts into tens of high-quality findings. So here I've broken up SCA into 4 different categories: manifest, log file, static analysis, and dynamic analysis. Each of these offer insight into a project's dependencies, just in slightly different ways and sometimes majorly different ways. But manifest files will tell you what direct dependencies are used and not much else. This isn't really at all effective these days. Some people still pin versions in their manifest files, but now we have lock files, which takes things a step further by also explicitly specifying a version for the dependency, but it'll also include any transitive dependencies used. So manifest and lock file analysis are what I often refer to as traditional SCA, whereas the industry has since incorporated other techniques like static and dynamic analysis. And I'm not going to argue static versus dynamic analysis in this presentation. We just don't have enough time for that. But you could probably guess that I prefer static analysis, especially in the context of software supply chain. And the 2 main reasons for that are build reproducibility is often a nightmare. With static analysis, at least how we're performing it at Semgrep, we don't necessarily care if your code can run. And B, I enjoy research at scale, and I can confidently run Semgrep against hundreds or thousands of projects without having to manually tune and reconfigure and solve all those bugs just to get the supply chain security solution to work. Whereas with dynamic analysis, I've found that's often to be the case. Oh, and of course, dynamic analysis is just significantly slower. That's a generalization, but in my experience, tend to be much slower. That said, there are some potential benefits to using dynamic analysis. The obvious one being that in static analysis, we can't determine whether a path is likely to or ever will be taken, which means dynamic reachability could be slightly more effective. But based on the research I've reviewed, the complexity tends to cause static analysis to be favorable, just because you run into so many headaches, whereas static analysis is still blocking out enough noise for it to be palatable, and you don't have to deal with all those issues you run into when deploying a dynamic analysis tool. And that's ultimately why at Semgrep, we use a combination of manifest, lock file, and static analysis. This gives us the best bang for the buck, and that enables effective reachability, but without compromising performance and usability. Again, at the end of the day, if we don't have security tools that people want to use, then people will always be less likely to improve security at all. So let's dig into reachability. And I briefly described reachability earlier, but we should narrow in on this because similar to SCA, the industry seems to be using it to mean all different types of things, which is really a frustration point for me, but I won't let it get to me. But just as an example, CDXGen, the open source Cyclone DX SBOM generation tool, calls a dependency reachable if it is used at all in your code. So you can tell this is different than vulnerability reachable because, well, one, it's not identifying vulnerabilities. It's just saying, hey, in your SBOM, you have this dependency, and now we know that you're actually using it somewhere in your project. You'd be amazed how often it's not the case that a dependency is used in a project, but is still within the SBOM or maybe specified in a manifest file. But other tools may call vulnerability reachable if it impacts a direct dependency, or maybe it's affecting a public-facing application. Now, Semgrep's reachability, which we commonly refer to as code scanning reachability, does as the name implies. It scans your code to identify where and how often, or often how you are using the vulnerable function to ensure that it's a vulnerable use case. If it is, then it's classified as a reachable. And this has been proven, time and time again to be effective. But to reference some external research, there is a paper by NC State titled A Comparative Study of Vulnerability Reporting by Software Composition Analysis Tools, which found only 2.1% of roughly 2,500 vulnerability alerts were found to be reachable through static code analysis. And early on, we conducted an internal study specifically for Semgrep's reachability, and that evaluated 1,100 open source projects for dependency vulns. And of these, Semgrep identified 932 total vulnerabilities, but only 12 were in fact reachable, which is actually less than 2%. But keep in mind, there are several factors that may play a role in your results, most commonly the language of the project. For example, JavaScript, Python, Java itself, their dependencies tend to benefit a ton from reachability. And I chalk that up to just be due to their modularity. Whereas other languages like C# are more likely to be used by standalone projects where static code analysis is less capable of determining function calls. So now that you know what reachability is, let's go over our workflow to give you insight as to how we produce quality rules. And I'm going to simplify just because it can be a relatively complex process depending on certain nuances. But in a nutshell, our researchers review every new security advisory impacted by supported ecosystems. We first take a look at the advisory, then take a look at the affected project. And there's often a lot of unknowns after this step, which leads us into the fun part, where we reverse engineer the patch PR, review documentation, and really just whatever it takes to identify the vulnerable function, as well as any other paths that may trigger the vulnerable function. And if you're wondering, it can be a ton of work, but the value is that our researchers only have to do this once, and it impacts all of our customers. So a one-to-many is definitely a favorable result. But once we've got it figured out as far as what the vulnerable function is, we classify the rule into one of three categories, which are always reachable, code scanning reachable, and manual review. And the names kind of imply their purpose, but basically, if the vulnerability impacts all likely usages, we'll label it as always reachable. If it's a subset of vulnerable functions or the vulnerability trigger is present in the code, we'll write it as a code scanning reachable. And if the vulnerability is triggered by a non-code value, maybe something like what operating system the package is used on, we'll label it as a manual review. But we do provide clear instructions just so you can quickly determine if it's relevant. So hopping on over to the demo, I'll be walking through three different perspectives. The first being a security researcher, and the second being a security engineer, and then the third, a developer. So hopefully you can see my screen here, but I have a GitHub security advisory pulled up, and this is a arbitrary expression injection in the pillow package affecting the pip ecosystem. And so the first thing I'm going to do as a security researcher is take a look at the advisory. What is the description? Well, we could see the pill.imagemath.eval function in Pillow before version 9 allows evaluation of arbitrary expressions. And they have an example here, imagemath.eval exec exit. So this does look like it just is a relatively well-written advisory. You'd be amazed how often these descriptions just say there's a vulnerability. There's a remote code execution. Don't worry about where. Hopefully you'll figure it out, and hopefully you're not impacted by it. But in this case, they do specify what the vulnerable function is. And so the next step as a researcher is to get an understanding of how this project is used. So I often go to the repository for the project itself. I'll scroll around, read some documentation, just get is this vulnerable function likely to be used by this project? Is it a core element or core component of the project? And then I like to take a look to see, how widely used is this project? I can look at the dependents tab in Insights, or I can just do a simple query for import pillow or from pillow, which are going to be the two common import methods. And we can see 900,000 files are doing either import or from pillow. So this is definitely going to be a widely used project. And since we know it's only a particular vulnerable function, we can actually get a general idea of how effective might reachability be. So if we do another query for the actual vulnerable function itself, we can see we narrow down to 570 files. So even without looking at things like what version of the dependency are you using in your project, we can already tell that reachability, specifically code scanning reachability, is going to be super effective for this advisory. And so the next step would be to take a look at the PR, which I got pulled up here, and we can see the actual patch itself was done right here, and it's only impacting the image math function, which can be directly called. So just for the sake of time, the other thing that we have to look for is any other internal functions or other exported functions that may indirectly be calling image math. or image math eval. But we know in this case, just because I've done the research in the past, that this function is not indirectly called otherwise. So our semgrep rule will only have to look for the image math.eval function. And so the next step as a researcher would be to hop into the Playground instance. And I simplified this rule just a little bit, but we have some internal tooling that adds in things like what is the dependency name and what dependency versions are impacted, message details, because our researchers will also update the advisory messaging. But for the sake of showing Semgrep here, I have a very simple rule, which you can see specified by the patterns label. And then I have a pattern inside for the import pillow. And so this is specifically going to look for the importing pillow. But note that in my pattern inside, I use import PIL. And in the code that I'm going to be testing against, it's from PIL. Well, ultimately, that's what Semgrep stands for. It's semantic grep. So we're going to be searching for the import method, but Semgrep, through semantic evaluation, is going to determine that from PIL is equivalent of import PIL. And so it'll still flag a match. Now, if I highlight this out and I run the Playground instance, you can see that it does exactly that. It finds the import method, and then the ellipses here will just say match everything after that. So to narrow in further from there, I use a pattern, and I look for the specific vulnerable function call. Again, the ellipses just means if anything can be sent as a parameter, and we'll still want to flag it. And we can see it narrows in on just the vulnerable function usage. Now, what's actually neat is the way that this is set up. Semgrep is smart enough to know that pillow.imagemath comes from the imagemath class that's imported from pill. So we can actually just remove this entirely, and we'll still get the intended results. Now, another thing I like to show off is just the turbo mode, because it helps us with our analysis a good bit, where we can actually make these changes in real time, and the highlights occur in real time as well. And so that's more or less it from a security researcher perspective. The next step would be to use that internal tooling and add all the necessary metadata fields, and then we push it out to our customers. And so any customer using the Pillow package and an affected version, they will either have an unreachable or a reachable result due to that. Now, looking at things from a security engineer's perspective, they're likely to spend most of their time in Semgrep app itself. So here's just my test organization that I set up for this demo, where we have a dashboard. We can jump into projects. I just have the one project here, which is a JavaScript application. And you can see we have 92 code findings, 18 reachable supply chain vulnerabilities, and we identified 3,400 scan dependencies. So let's jump into the reachable supply chain vulnerabilities. And here we have 18 vulnerabilities, but we have 51 unreachable and 34 undetermined. So just to add some clarity here, unreachable means that we have a code scanning rule in place, and we just didn't find the vulnerable usage in your code, which means you can almost always say that this is not a prioritization. We really shouldn't be spending time patching potential vulnerabilities in our code that we know we're not even using the vulnerable function for. That was maybe a bad way to explain that. But basically, you're not using the vulnerable piece. Upgrade if you'd like, but it's probably not a priority. The undetermined being 34 is likely due to the fact that at Semgrep, we only write reachable rules for criticals and highs. So if we toggle off medium and low, we can see we're now down to 4 undetermined, and those are going to be those manual reviews. So just to give you an idea, you can scroll through, you can get a gist of the advisory message, you can check out the description just to get more context. You can also see the actual source rule that we're using in our code. So in this case, it's just a always reachable rule. Or now if we go down to a code scanning rule, we can actually see the Semgrep patterns that our researcher wrote to identify the vulnerable usage. And within the app, you can triage, you can label as false positive, no time to fix, susceptible risk. You can also filter out say you don't want to worry about transitive dependencies, which make up more than 90% of a typical project's vulnerabilities, you can do that here. And yeah, ultimately, oh yeah, one last thing to note. If there is a code scanning reachable rule that finds the vulnerable usage in your code, you can use the link here and it'll redirect you straight to where that vulnerable function is being called in your code. Now, lastly, I'll get into the developer's perspective. Now, I like to think developers don't really want to spend a whole lot of time with security tooling. I know security tooling is awesome. I love it as a researcher. I want to play with them all day long. Developers probably don't want that experience. So we do have the CI/CD integration, which I put into this test project on GitHub. And so I have a single pull request, which I'll click into. And so you can see first thing to note is that there's these PR comments. So it saw that I was adding a vulnerable function call to vm.run as a known vulnerable function. And you have the risk here so the developer can see the risk. They can also see the fix, which is often just going to be upgrade the library, at least for supply chain vulnerabilities. And then if they are interested in learning more about it, they can go to the references. They could also ignore this finding if they're confident that it's maybe a false positive. The other thing I like to highlight here is just the speed. So Semgrep actually completed in less than 1 minute for this CI/CD action. But yeah, so that is the demo. Let me hop back over to the slides. And so hopefully that sheds some light into how important SCA is for prioritization. But what's subjectively more important than discovering vulnerabilities is going to be remediating them. Sonatype's 2023 report discovered that 96% of known vulnerable downloads had a fixed version available already. So that's a pretty good sign that open source project maintainers are doing a good job of releasing fixed versions. And so this little image here suggesting that it's a random person in Nebraska, you really should be thanklessly or praising them for all the glorious work they're doing. Log4j is a good example where Sonatype actually has a dashboard for known vulnerable downloads. And they've had this since, I believe, September or December of 2021. And so since December of 2021 specifically, they've had over 300 million vulnerable downloads of the Log4j package. And still, in the last 7 days, roughly 25% of all downloads were vulnerable versions of Log4j. So, I mean, there's a fix available. People just, choose not to use it. I'm not saying that all those downloads are using it in a vulnerable way. There are ways to use the Log4j vulnerable versions without introducing risk into your environment. But best practice, always keep those dependencies up to date. And so we'll focus on what orgs can be doing better to alleviate some common struggles with remediating vulnerabilities, besides the obvious ones, which are used to use some form of supply chain security tooling. And so in the remaining slides, we'll touch on semantic versioning, manifest files, and transitive risks. All right, so semantic versioning is really beautiful. I love it so much. I mean, I just wish there was a way to enforce it. But today, it can be super beneficial for identifying easy wins during the remediation process. For example, maybe you have 200 vulnerabilities, but 100 of them have a fixed version that is just a patch upgrade. Now, if I was the responsible developer and saw this, I'd probably just hit the upgrade button and pray, although I maybe wouldn't suggest this on anything important in prod. Maybe an additional 50 are minor upgrades. Again, if you're me, I'm just going to spray and pray. But if you're a responsible person, maybe pay closer attention to the minor upgrade versus the patch upgrade. There's patch, minor, and major upgrades. None of them definitively have to introduce a breaking change, but as you go up the chain, it's more and more likely for it to occur. And so major upgrades, that being said, are the ones that I actually do definitely want to take a look at. I'll review the change log, relevant documentation, release notes, whatever that might be. And that's just because I've been bitten more than once by major upgrades, breaking functionality, or really the nightmare is it changes functionality and just enough where it only slightly impacts your project and you don't have a test case for it. So now you just have this changed functionality in your project. You but you don't even know about it. It's not like raising any red flags, not producing any errors, things like that. And lastly, just a reminder that most of what I've shared in this presentation is very ecosystem dependent. So breaking changes may be more common in some languages than others. There is actually an example study called Breaking Bad, Semantic Versioning and Impact of Breaking Changes in Maven Central that concluded roughly 20% of non-major releases in the Maven Central ecosystem were in fact breaking changes. But that's still pretty good odds. 80% likelihood that semantic versioning is being followed. So now, if you're a JavaScript developer, you've likely seen a package.json file, otherwise known as your project's manifest. And if you're developing in a different ecosystem, you'll likely have a different file name, but the same concept more or less applies. A manifest file contains all direct dependencies used by your project and is what is used to generate a project's lock file. And we touched on what that was a bit earlier when discussing SCA. But as an example, whenever you run npm install or directly generate a lock file with the package lock only flag, npm is looking at your manifest file. It looks at the version ranges assigned to them, and then assigns specific versions to those dependencies. And that'll also determine all of the transitive dependencies as well as their respective required versions. Now, what most people don't realize is the potential ROI when you keep a manifest file up to date, especially when paired with meaningful version ranges. So for example, a dependency that is widely used throughout your project, you may want to actually review all changes before upgrading, but a package where you're only using one component of it, or maybe you know it to be a well-maintained project, you can usually safely assign a broader version range. So back to our example with npm, you can get fairly creative on how you specify versioning for each direct dependency. But to quickly go over some common ones, you can specify an exact version, use a tilde to allow any patch versions, use a caret to allow both minor and patch versions. So basically anything except a major version. That's probably the one I would most commonly use. Or you can always go for the latest version via an asterisk. And that's one I'm going to use if it's a dependency that maybe I'm only using a small piece of, or I'm confident that the functionality is not going to change anytime soon. And just to show you a quick example of what this might look like in Semgrep app, you can clearly see your version and the fixed version. So you see it's just a patch or a minor upgrade. Well, in that case, it should just be an easy one. You can go ahead and upgrade that dependency. But there is a research paper titled A Large-Scale Analysis of Semantic Versioning in NPM, which reported that for the NPM ecosystem, the minor flexible version specification was by far the most commonly used. And the study also determined that over 87% of all dependencies in their test sample were configured to receive updates automatically. But that doesn't mean they actually get updated automatically. There is a common occurrence when there's a new version available, but you haven't updated your lock file in a while. So of course, this can be resolved by just regularly running npm-i or similar to really just regenerating your lock file, however which way you want, either npm-i, npm install, same thing, or just the package lock only flag. All right, and so I'm going to be ending things on a very controversial topic. It's also maybe my favorite topic, and that's going to be transitive vulnerabilities. And these are basically the dependency vulns impacting your project's dependencies. So I often refer to them as third, fourth, or fifth party vulnerabilities, but the chain can go on much further than just 5. And in fact, it very commonly does. A little fun fact for you, there was a 2020 GitHub Octaverse report that disclosed that the average amount of indirect or transitive dependencies for a JavaScript project with 10 direct dependencies is 683. So I always found that to be absolutely mind-boggling. If you're only bringing in 10 direct dependencies, you're only doing 10 import statements or require statements, whatever it might be, you are actually taking code from perhaps 683 different projects or packages. Now, the biggest reason why transitive vulns is such a controversial topic is because in reality, I mean, what are you going to do about it? I hate to say it, but if you can use a dependency maybe affected by another dependency's vulnerability, there's really not much you can do. I mean, unless you plan to dedicate engineering time to fixing the issue however far down the chain it is, and then applying the fix at each and every level in between. That's you're going to need a whole company, not just a small team, to dedicate time to doing that. That said, I do really enjoy the research behind transitive vulnerabilities, which is why it's perhaps my favorite topic. But now you might be thinking reachability would be super effective at this. However, reachability via static analysis, at least, hasn't really impressed me for transitive vulns. This goes back to what I mentioned earlier about active versus inactive code. So for example, if I only import one function of an NPM package, transitive reachability via static code analysis won't know to only look at paths associated with that particular function I imported. And that has a chain effect. So as you go down the dependency tree, there's likely to be more false positives than you might hope for. But at the end of the day, transitive risks are definitely real. And I'm hopeful future research and development will continue to make these more manageable by identifying if and when the risk applies to a particular project. So at the end of the day, odds are that more than 90% of your vulnerabilities are caused by transitive dependencies. And I say just smack the easy button and ignore those transitive vulns altogether, at least while you still have direct dependencies with known issues. So to wrap things up, I'll leave you with the three main takeaways, in my opinion. Firstly, the effectiveness of reachability. We routinely see up to 98% of false positive reduction thanks to code scanning reachability. Secondly, build reproducibility and semantic versioning solves so many headaches. It's only inevitable with the recent push for software supply chain security that we see these become more of a priority. And lastly, the spicy take, which we just went over, transitive vulnerabilities, they can usually be ignored. I say usually because there are some very, very special cases, but even then, if you're using respectable packages, they themselves will often create a security advisory due to their usage of a transitive vuln, which ultimately makes it a vulnerability impacting a direct dependency, in which case reachability will be very effective. So this could very easily start a debate as to why current standards for reporting supply chain vulnerabilities is ineffective, but let's save that for another time as well. Great, yeah, thanks everyone. And I do have some resources on this slide if you're interested in learning more about Semgrep's reachability or the Semgrep product as a whole. And if you're interested in subscribing to Crime Hacks, my weekly software supply chain security newsletter, please do so.